thread. Okay. The idea of a thread is that when a process is created, okay, without in normal situation, a process created, it has a program, has a code associated with that, right? And then we started running the code, okay? and this is an execution flow, like active. So there's an activity in the process. Okay? A thread is we can treat a thread as a execution flow inside a process. So it's like a thought, okay? So it means you have a process. It's like you have a body in there, okay? And with a thought, then the process become active, okay? Without a thought, then it's just a body, just a program, just a body there, okay? A thread means if a process has one or more threads of execution, if that a body contain multiple thoughts, then this multiple thought, they are doing their own activities. It's possible, okay? Then this kind of process we call it multi-threaded process. You have more than one active execution flow simultaneously existed. It's like person has two personality and they simultaneously existed. Okay. Some people, if it's mind mix up, then it become multi-personalities. Okay. It's like multi-threaded process. Okay. Two activity coexist simultaneously. A program can be so if an operating system is thread aware, that means operating system can keep track process and also keep track threads, okay, within the process. Okay, so a thread aware operation not only keep track process by the PCB, okay, process control block, and each process controller also keep track a list of thread control blocks for the particular process. PCB keep only thread specific information, okay, because process is like a body, right? The soul, they share this same body, but they have their own minds, okay? And the thread specific information like CPU registers, program counters, stack pointers, and scheduling informations, those are maybe different, okay? Because different thread may have different priorities, okay? And the other informations of threads in the process usually they are shared, okay? And so those shared information or attributes, they are kept in PCB, okay? So multi-threaded process and operating system usually maintain this data structure of PCB, okay, as a list of PCB, and then each PCB they contain a list of TCB, okay, and TCB in general they contain thread ID because inside a process you need to have a thread ID to specify which thread, okay, activity of a particular thread, and CPU registers of that particular thread and other thread specific attributes, for example, signal mask and scheduling parameters and so on. Okay. Conceptually, it's something like this: a single threaded process, that means inside a process you have a code, your data, your file register, stack, and so on. Those are the static part. Is like a body, and you have single soul inside there. So, okay. But for a multi-threaded process, the code may be the same. The data and the file, okay, the instruction data and files, they are the same. But each thread has its own registered data and stack and program counters and so on. Okay. So it's like you have a single body with multiple doors, and each door is it's online, right? On status, program counter, and so on. Okay. The reason for multi-threaded is that sometimes an application is complex, so we allow have multiple activity, and this activity they don't have very specific dependency relation, so you can execute them in any orders. So that means they are concurrent. So for this using this multi-threaded mechanism, then the application may be running much faster or much naturally. Okay. For example, when we control an elevator, okay, the elevator has a panel, okay, outside each floors, okay, and usually this panel contains at least two buttons. One is up, one is down, okay. And if the building is 10th floor, then you have 10 control panel, and every control panel has two buttons, up and down, okay. And inside the elevator, we have a panel, okay. List, they have for 10th floor, okay, building, they have 10 buttons, okay. At least for each one, with a floor number associated with that, okay. So inside any elevator, you can touch any button to specify you tag it, okay. So you can see that we have 11 panels, okay. Every floor has a panel, and inside elevator at least you have a panel, okay, with 10 buttons, okay. And this input device, these panels, they can all accept the input simultaneously, okay. So if we design this elevator controller in a way that by using single-threaded process, then we need to scan this panel, input panels, sequentially, one at a time. And then after one cycle, you scan all the panel. Then you decide how to move this elevator to the next destination. Okay. And this scan, you need to pre-design a specific order to scan. Okay, right? So after one scanning loop, if the person just hit the button and immediately after the scanning, then this button input need to be recognized after in the second scan loop. Okay, but every scan loop, after the scan loop, the elevator may decide to move up. Okay, so for example, the elevator is in the second floor, but because there's no one is waiting in second floor, also there's no one inside of elevator, no one want to dip in second floor. So the elevator just decide to pass through this second floor. So after this scan, loop if before and then the elevator just decided to move out of the second floor. Okay, for example, it moved down from the it's in third floor, but after scan, then it decided that it will skip first floor, second floor, and directly to the first floor, for example. And after this scan, the one person in outside the second floor is hit the button, but unfortunately, the scan is already been done, so the person outside this second floor will anticipate that although the current floor number, okay, usually in every floor you have you may have a indication to specify, so the current location of the elevator, for example, they show 3 in third floor, and then you hit the button, but the elevator just passed through, did not stop in second floor. So so sometimes you are unlucky, so you will face this situation. But if we use multi-threaded process instead of scanning these panels in a sequential way, every thread is scanning its own panel, okay, and record this result into this shared data. So whenever you receive the content, receive the input, it record its input immediately. So you may have 11 threads which control, accept the input, and you have another thread control the elevator actions. Okay, so these elevator actions they can, whenever they find out there's an update from some, they can make the decision according to that. So it don't need to go through this predefined scheduling, the scanning. Okay, the control elevator controller, okay, always immediately get the input from the particular thread immediately. Then the decision may be much friendly to the users of the elevator. Okay, when you find out everything in third floor, and then you hit you are in second floor, you hit the button, the input immediately enter, and so the elevator controller will receive much quick than this, maybe much quicker than this scheduled scanning. Okay, and so the response may be much efficient. So the elevator controller will decide they will stop in second floor. Okay, because there's someone waiting there, and so on. Okay, so this is multi-threaded and single-threaded processes. Okay, the difference is that you may have allowed multiple activities simultaneously coexist inside a program. Okay, they use the same code. The purpose for this multi-thread is because they cooperated in some way, and then they accomplish to the same goals. Okay. For threaded multi-threaded process, those threads they will share the same instructions segment, data segments, static and global data are shared, and uninitialized data part also shared. Open file descriptor are shared. Okay, signals, defined signals are shared. Current working directory, user group IDs, okay, are shared, but they have individual, each thread may have its own attributes, ID, thread ID, set register, stack pointer, program counter, stack value. Okay, because each thread is and activity. So inside each thread, they have their own subroutine call stacks. Okay, and signal mask, different thread can mask out different kind of signal and priority info and so on. Okay. Advantage of threads, like we say, it may be more efficient. Okay, and not only in the long term, but also in the memory management, memory utilization part, because create a new thread inside the process is much efficient or much than create a new process. Okay, because you don't need to create those shared part of the memory maps. You only allocate some memory, some data structure, TCP. You don't allocate a whole PCB for a new thread. You allocate a TCP for a new thread. Okay, so the resource used by system is much less than a new process. Okay, and also because those code and data segments are shared. Okay, so those parts can be shared by the same different threads inside the same process. And also because there's memory map, there's a part of memory map are shared, okay, because the BSS and the data part are shared by threads. So they can use this shared part to doing some communication. So shared memory become automatically exists. So they don't need to use the other inter-process communication mechanism to communicate with each other. So those threads inside the same process, they can just use their shared memory data structure to communicate. And if the system has multiple processors, then every thread can be executed by different CPUs. So program maybe become scale if with number of CPUs increased. Okay. And also multiple core system. Okay. They can take advantage of this. To implement threads, we can either implement as a kernel level thread. That means the thread is supported by operating system. So operating system handle the scheduling, creation, and synchronization of the threads. Or maybe threads are implemented in user level. That means we use a strict thread library with codes for creation, termination, scheduling of threads. And kernel see the operating system only see a process. Okay, so operating system schedule process, and the user level thread library schedule threads inside process. And these threads may be preemptive or non-preemptive, depends on this thread library. Okay, the user level thread scheduler. Okay, and also it's possible we can implement a thread by hybrid mechanism. Okay, that means use user level thread library on top kernel thread. Okay, so operating system support thread, and also using user level thread in user process. So user process use when they try to create thread, they use user level thread library to create threads, and these threads may be mapped to the kernel thread, okay, by using one-to-one mapping. So every user thread is mapped to a kernel thread, okay, or end-to-one mapping. User threads, the process, the threads from the same process, they are all mapped to one single kernel thread. That is like a user level thread. Okay, so operating only see a kernel thread. Okay. Or last one is a more general mapping, is really hybrid. So the process may have n user level threads. Underline, this process may occupy n kernel threads, and this n usually is greater than m. Okay. So this we call it hybrid thread model. Okay. So operating system has thread, kernel thread, and these kernel threads, how to use this kernel thread depends on user level thread library implementation. Okay. The user level thread library may map the whole process into one kernel thread, or map a process into several kernel threads. Okay, and this n to m mapping. Okay, that means that for example, if a user process may have 10 user threads, but the user level thread they occupy 3 kernel threads. That means this 10 user threads can have at the most 3 threads are running concurrently, are scheduled by the operating system simultaneously. But the other 7, they will compete for these 3 slots of the scheduled entity. Okay. The advantage of user level threads is that because the implementation is much easy, low cost, because the operation is in user mode. They don't need to create a thread. You don't need to switch it to kernel mode and whatever. And the scheduling are easy to be replaced or customized, because the thread library has its own thread scheduling, which can be optimized to a particular task. Okay, so when you create a user process, and inside the process, when you create a thread, you can specify these threads. They are scheduled by different scheduling algorithm. Okay, associated with the thread creation, and also much portable, because for different operating system, you can use the same user level thread to port to there. If the implementation of this user level thread, they follow some standard APIs. Okay, and the disadvantage is that if a thread is blocked, all threads for the process may be blocked. Okay, unless some asynchronous I/O call are supported, or this user level is a hybrid. Okay, so pure user level thread, of course, the one thread blocked, the whole process is blocked, because it's only mapped to one kernel operation schedule process as a whole. So any thread is blocked. Okay, unless these threads they did not use synchronous I/O operation. They use asynchronous I/O operation, so will not be actually blocked. Okay, and so the other thread can continue to use the CPU time when its time quantum is not used up. Okay, and so. And of course, for user level, pure user level thread, multiprocessor cannot be the advantage of multiprocessor cannot be taken off. Okay. In POSIX, they also define the thread APIs. Okay, it's called P threads. Okay. In POSIX.1c thread extensions. Okay, in 1995, okay, they have created this extension. They define API for managing threads, and this Linux, Solaris, Mac OS, NetBIOS, BSD, FreeBSD, they all support pthreads. Okay, and Microsoft Windows pthread API library on top, Win32 API is also you can use this. Okay. The thread lifecycle management API include this pthread attribute initialize thread attribute and create a new thread, join, wait for termination of other threads in the same process. Okay. So that means when a thread try to synchronize the execution, it may need to wait other thread terminate or whatever. Okay, so join means that exit terminate itself, cancel terminate the target thread. Okay, and all these thread functions must be compiled, linked with this pthread option. When you use a POSIX thread, your compiler or during the compilation, you need to use this option. Okay. Threads are concurrent if they exist at the same time or process, okay, in the same system. And these concurrent threads or process, they can be either independent or cooperating. Okay, threads inside the same process usually are cooperating threads. Okay, they are concurrent, but they are cooperating. Otherwise, you will not create those threads inside the same process. Okay. But threads in different processes, usually they are independent. They may be independent or cooperate, depends on those processes, they are cooperating or independent. Okay, so independent threads, they don't have dependency relationship with each other. So the execution of one will not affect the others. Okay, but cooperating threads or process, their execution can affect each other's. Okay, so you need to have a way to synchronize these cooperating threads or process, so they will behave well. Okay, because they need to coordinate in some way. So the synchronization is used, required to coordinate the layer operation, their layer execution. Okay. The reason is that here is some typical reason example that the cooperating process of threads, they need to be synchronized in some way. Okay, cooperating threads may access shared data simultaneously. Okay, because they are cooperating, so there's some information they are shared. Okay, and this sharing concurrent access may create some inconsistency. Okay, so if the consistent result to generate the result which is meaningful or consistent, if depends on the data access order, then this condition may occur. Okay, so data consistent need to be maintained in some way, that if the execution of or access of this shared data in some well-defined ways, okay, by using mechanism synchronization to enforce that. So otherwise, the result may become abnormal or unexpected. Okay, those are so we call risk situation, risk condition. Okay, here is an example of this condition. Assume you have a bank account and the current bank balance is 1,000. Okay, when you withdrawing 500 from an ATM machine, in the meantime, your parent transfer 5,000 to your account, and these two things happen simultaneously in the same time. So we have two operations. Okay, one is withdraw, and the operation or instruction of to implement withdraw, usually we require at least 3 low-level operation. One, you read the current account balance and subtract 500 because you try to withdraw 500 and write the account balance back to the account. Okay, these three operations. And then for transfer 5,000 to your account, it means deposit. Okay, you need to read the account balance and add 500. Okay, and write the account balance back to the account, right? So every high-level operation, withdraw and deposit, will contain three low-level instructions. Okay, and because these two high-level operations, withdraw and deposit, are concurrent, simultaneously happen in the same time. So eventually these 6 instructions, the execution order of these low-level instructions may be mixed in a way that the result may become either 5,500 or 500 or 6,000. These three are all possible results. To get but the meaningful or correct answer should be 5,500 instead of 500 or 6,000, right? The current balance is 1,000. To get the result of 500, that means the deposit, after the deposit, the rebalance of the deposit, the withdrawal also read the current balance. Okay, and after deposit finish its right account balance, the withdrawal right its account balance to the account. So the final result become 500 because of the right account balance, the instructional right in of the withdrawal is the last one, and the read account balance of the withdrawal is the first one. Okay, for example, that. Then the result will become 500. To get a result of 6,000, you may, if the deposit, the read account balance of deposit is the first instruction, and the write account balance of the deposit become the last instruction, then the result become 6,000. A race condition typically occurs when 2 or more cooperating threads try to read and write shared data concurrently. Okay. Those instruction or region of the program, those code segment, code regions, that try to access shared resource and cause race conditions. And those region of code we call critical sections. Okay. In here, in this particular example, this 3 withdraw and deposit, they both are critical sections because this 3 instruction code segment may affect the result. Okay. To avoid risk condition, if we only allow one thread at a time to execute within the critical section. That means in this example, the withdrawal is the whole three instructions of withdrawal are finished before the deposit, or vice versa. The result will become 5,500. Okay. So if the critical section of different threads are executed sequentially, then the result, well, the race condition can be avoided. Okay. So race condition can be avoided by using lock with critical section. A thread must acquire the associated lock before entering critical section. When leaving the critical section, the thread must release the associated lock. Okay. And if the associated lock is not ready, the acquiring thread need to be blocked outside the critical section until it got a lock. Okay. So the original example will be if we use critical section with lock, then the withdrawal will be replaced by we enter critical section, acquire lock, release lock. Okay, covered by using these two instructions to cover the critical section part. Okay, and the deposit also they use before really deposit the acquire lock, and after write balance you release lock. Okay, then we can guarantee that this concurrent execution of the threads withdraw and deposit. Okay, the result is always 5,500, right? And this is consistent. Okay. The critical section, the problem. Okay, if we use critical section and then we use with a lock. Okay, so the solution for this critical section problem, so associate the lock to manage the lock properly. Okay, then we need to usually this critical section. The solution for this critical section usually will require these features. First, mutual exclusion. Okay, that means no more than one thread may be inside the same critical section. Lock is one way to implement to have solve the problem of critical section. Okay, but you may use other ways.